So here we calculated in the previous example, we just calculated the candidates for the optimum values, and we then got the value of the function at this point, and it was giving us the two same values. That was the 2 square root of 2, and so we could conclude that the 2 points were both minimum values. Okay, but if ever you are in a slightly more complicated setting and you still want to get something that is giving you the nature of the critical points that you have found, we're going to have second order conditions, just like when we were doing unconstant optimization. So we have this problem optimization, minimizing a function f subject to one constraint g of xy is equal to 0. We write the Lagrangian. We solve, well, we look for qualified points and unqualified points, and we solve the first order condition for the qualified points. So the gradient of your Lagrangian is equal to 0. If ever you've got unqualified points, you should study them separately, and then either you just compare the values you get for the solutions of these first order conditions, or you can use a second order condition, which is going to be on what's called the bordered Hessian matrix of the Lagrangian, which looks a lot like the Hessian matrix of the Lagrangian with respect to all its variable. Okay, so we've got the three variables, the x, y, lambda, if we've got the two variables plus the lambda, the Lagrange multiplier. Okay, so what does it look like? If you make the Hessian of this gradient, well, of this Lagrangian stuff, what are you going to get? So if you just do, so you know that in your Hessian matrix, you should have derivative of order 2, derivative of order 1, that's the gradient that I have. So the gradient was df over dx minus lambda dg over dx. Then we would have df over dy minus lambda dg over dy, and then we would have the last thing, which actually we're going to rewrite minus lambda with respect to lambda. We would get minus g of xy equals to 0. Okay, well, minus g of xy, that would be the derivative with respect to lambda of your well, okay, yeah, I wrote here with we should have a minus here, but it doesn't matter if we want it equal to 0. It's the same thing. It's minus g of xy equal to 0. This is what we, but actually this sign is important when we put it in the Hessian, in the bordered Hessian. Keep in mind that if ever you choose minus lambda or plus lambda instead of minus lambda, as long as you're consistent, it remains the same. So if we do the Hessian matrix of this, what we're going to get, so we should take the first item and differentiate it with respect to x, y, and lambda. So with respect to x, we get d2f over dx2 minus lambda d2g over dx2. I should differentiate this with respect to y, d2f dy dx minus lambda d2g dy dx, sorry, and with respect to lambda, that's my third variable, so x, y, and lambda with respect to lambda minus dg over dx. Okay, we do the same thing for the second row, so we get, of course, something that is going to be symmetric, so d2f dy dx minus d2g lambda d2g dy dx. Okay, we get with respect to y again d2f dy square minus lambda d2g dy square, and with respect to lambda, that's just remaining dg over dy. Okay, and then we do the same, we differentiate that last one with respect to the three variables, so with respect to x, dg dx minus dg dy and 0. Okay, so that you will always have something looking exactly like this, meaning here you've got some a square part, which of course your matrix is again symmetric, that's a Hessian matrix. The square part where you've got the partial derivatives of f and g, and you have this border where you get the opposite of the gradient and the gradient transpose of your constraint. Okay, so that's, so here I've just written it with the Lagrangian instead of all the details with x and with f and g, and that's it. That's bordered because here you've got a square with the second order derivative in x and y, and you've got your border, which is this one, your border, the minus the gradient of g on the gradient of g written as a row matrix that you've got here. So that's why it's called the bordered Hessian, but it's really a Hessian matrix for your Lagrangian function. It's really, we really did the same thing. We differentiated with respect to x, y, and lambda, and x, y, lambda. Okay, and it's always going to have that shape with the 0 at the bottom and the gradient minus the gradient of g appearing at the two rows that are at the final row and final column. All right. Where is and then okay, we're going to get a very nice condition is that very easily, much more easily than when you are unconstrained, where you had to calculate some eigenvalues here. The result is much faster. You just make the determinant, and if it's positive, then you've got a maximum. If it's negative, you get a minimum, and if it's equal to 0, you can't conclude. Right? Where is that coming from? So here you've got the details, but maybe you can take some time to read them. The idea is, again, the same thing. We are still interested in the sign of this second order term, because that's giving you, in the end, when you've got a critical point, it's giving you the difference of the value between the critical point and the surrounding points. So we want the sign of this, but not for any kind of HK. We just want the one that are staying on the constraints level line. Well, on the constraints, okay? And this is where, if you want to prove that, you can use what we saw last year as the implicit function theorem, is that for your constraints, so g of xy, if you're looking at the curve j of xy is equal to 0, then you know that you can find locally, if your derivative is not equal to 0, one of the derivatives is not equal to 0, you can locally express that as x phi of x. Okay, you can express y as a function of x locally. All right, so we see that was the implicit function theorem. So we know we can find a function phi such that this is happening, and then we have some relation between the dx and the dy, and the dx and the dy are the ones that are appearing here. The increase in x, the increase in y, these are the ones that are appearing here. And so if you look at, if you make the calculation, but only for the dx and dy that are defined using this relation, okay, you will find that actually this is corresponding exactly to the determinant of, well, it's the opposite of the determinant of the Hessian matrix. Okay, so that's the proof. Just to tell you that the magic does not come from nowhere. It's just appearing for very good reasons that you can absolutely analyze completely. You've got all the math for that, but then you have to remember how to use that. If the determinant of this bordered Hessian is positive, then we've got a maximum. If it's negative, we have a minimum. And just to get back to the example we treated, for the example, we just obtained, where was that? We just obtained the two solutions, and then we said, well, these are minimums, but actually we just found the critical points, and we calculated the value, and geometrically it made sense that they would correspond to minimum values. But if you were more in darkness to the problem you are treating, you would need to make the Hessian, the bordered Hessian. So that's the bordered Hessian you obtain from this one. Well, actually, from here we should have a minus and plus. Okay, it's the same one when you're staying at level 1. It doesn't matter whether you express it as minus g or plus g, but then when you write the Hessian matrix, this is what we get. So we've got this famous border where we've got the gradient of your constants minus the gradient of your constant and a 0 appearing here, and here you've and the square corresponding to the derivatives in x and y. Okay, so that's the bordered Hessian. So I wrote it the one without the signs appearing in red is the one corresponding to plus 2 square root of 2. If you remember, we had 2 square root of 2 and 2 as the points. And the one with the plus sign written in red corresponds to the choice of minus 2 square root of 2. And if you do the determinant of the corresponding two matrices, you get something negative in the two cases, all right? So that it does correspond indeed to the minimum values that we were expecting.